Hi, this is Randal Schwartz, host of FLOSS Weekly. This week, Aaron Newcomb joins me. We're going to be talking big storage, Ceph. It's got replicated data store. It looks like a file system, or it looks like S3. You're not going to want to miss this, so stay tuned.
Netcasts you love.
From people you trust.
This is Twit.
Bandwidth for FLOSS Weekly is provided by Cachefly at CACHEFLY.com.
This is FLOSS Weekly with Randal Schwartz and Aaron Newcomb. Episode 250, recorded May 1st, 2013. Ceph. It's time for FLOSS Weekly, the show about free, libre, open source software. I am your host, Randal Schwartz, Merlin at StoneAge.com, bringing you as often as I can each week. Well, each week, or as often as I can, the movers, the shakers, the big projects, the small projects that probably you're using every day and don't know anything about that. So we talked to some pretty fascinating people. And let's go ahead and bring on our co-host, Aaron Newcomb. Welcome back again.
Hey, Randal. Good to be here.
Yeah, so this is what, 3 weeks in a row for you?
Yeah, 2 or 3 weeks. I don't know. I kind of begged to be on this show, though, just because of the nature of the content.
Yeah, so tell us who our guest is today.
So we're going to be talking to Ceph, or about Ceph, I should say, which is a distributed storage system. And I've been working in the storage industry for a long time, so this is really interesting to me. But it's a system with distributed storage nodes. It does object storage. It does block storage. Really, really cool architecture that they've built. And it's all open source, so it's really, really interesting. Cool.
I'm looking really forward to talking to, I believe his name is Sage Weil, one of those. I'll have to ask him how that works. Storage is big stuff now. And I know a lot of people, when I announced the show, saying, oh my God, you're going to talk about Ceph? This will be great. I know we're going to probably want to compare it to the other things like Gluster and things in the same similar space. So we'll make sure to ask him all that. I just wanted to say also, happy 250. This is a 250th episode of FLOSS Weekly. I'm pretty excited by that milestone. I've been involved with all the episodes except for the first 17, although I was a guest on one of them. And so it's been, I'm really happy we made it 250, and I'm hoping to do at least another 250 more if the Twit network will let me. So, so thanks, Aaron. Thanks for being part of the program as well.
Yeah, sure. I started out as a guest as well. I was a guest on a couple of shows, and then said, hey, why don't you use me? I'm doing podcasts. And so that's kind of how I ended up here as well. So, Randal, you've done a great job shepherding the podcast along and getting the guests. So congratulations.
Thank you. Well, without further ado, let's go ahead and bring on our guest, Sage Weil. Well, I'm probably mispronouncing this. Is it Weil or Weil? Welcome to the show.
Weil.
Sage Weil. Sorry about that. I've probably been mispronouncing it for the last few weeks again, and I hate that when I do that because I hate it when people mispronounce or misspell my name. So I feel more sensitive to that.
It's been my whole life.
Great. And where are we speaking to you from? Where are you? Where are you speaking to us from? You don't know where we are.
Yeah. I'm in Los Angeles, West LA.
Los Angeles. Oh, I could have just driven over. I'm currently in the Howard Hughes building over by the 405. So.
Oh, nice. Okay.
Cool. All right, so enough chit-chat about where we are, and we can talk about the weather, but that isn't why I brought you on. I said we should really talk to somebody about Ceph, and you are the man. So I gave sort of the 30,000-foot view of Ceph at the beginning of the show. I think I did a pretty good job because I've been studying this for a while. But why don't you go ahead and give us what Ceph is and what problem does it solve?
Sure. Ceph is an open source, scalable, distributed storage system. It's designed for multiple use cases. It can do object storage if you are building a Flickr and just need to pile a ton of data into a cluster. It can do block storage, which is useful in the cloud space for storing virtual machine images or replacing your SAN or something like that. And it also has a scalable distributed file system that gives you full POSIX, NFS-like semantics. And it does this all using a single storage platform. But the key thing is that it's really built for scalability, so anywhere from 10 to 10,000 nodes, and it's open source.
So let's go back to those three different modes, because I think that's one of the really interesting features about this. So you have, I'd say probably the closest thing would be the S3 storage for object store. Is that a fair comparison?
Yeah. So Ceph actually provides two different object storage layers. One is sort of the native object infrastructure that the whole system is sort of built on, and it has It's a little bit lower level than what S3 provides. It's really designed for developers. But on top of that, we've built a RADOS gateway, we call it, that gives you S3 compatible API semantics. So it's actually compatible with both Amazon S3 and with OpenStack Swift.
Awesome. And again, staying still at the high level, I guess, and we'll dig into these a little bit deeper later. So the second one you said was disk block storage, was it?
Mm-hmm. Right. So the block storage interface provides you with a virtual disk, essentially, except instead of having an actual disk, it's actually striped across an entire cluster. So it can be a small disk, a large disk. It can be, and uses the shared storage resources of the entire Ceph system.
Also, I could actually mount it as a block device on my system, and it would look like a single disk drive or blocks of a disk, but somehow Ceph behind the scenes then replicates that across various systems.
Precisely. It could actually be stored on hundreds of drives or 3 drives, depending on the size of your cluster and the size of the disk.
And even things like replicating it out to make sure it's there's a copy that's not in the same data center?
Precisely, yes.
Cool.
All of those details are essentially hidden from you.
And the third one was, I forget already. Sorry.
File system.
Okay. And
so Ceph has a POSIX distributed file system. So you get files and directories, the usual sort of semantics that you get from Unix. But again, it's designed to be, petabyte, exabyte scale. So you can have a single namespace, billions of files and directories, all in a single file system accessed from multiple machines at the same time.
And I can add more to that by just adding drives and systems to share this on without having to tell like the operating system that it's getting bigger, or do I have to do something?
Precisely. From the client's perspective, it's mounting the cluster, but the cluster is managing scaling and so forth, and failure and high availability and all that behind the scenes. So you can add more storage, you can remove storage, machines will fail and recover, data might migrate, you might change the level of replication. All that stuff might be happening behind the scenes, but from the client's perspective, it doesn't really know any better.
And so how did Ceph get started?
It all came out of the research group at the University of Santa Cruz, mid-2000s. There was some funding from the Department of Energy for petascale file systems for their supercomputers. And that was sort of the genesis of a lot of the design pieces, the data distribution algorithm, the scalable metadata management, and then eventually the replicated highly available object storage. And then over the course of doing my dissertation there, we sort of put all the pieces together and built the entire system and named it Ceph. And that was,
wow.
It was open sourced in 2006, somewhere in there.
And so from there, how is it being used today? I understand there's a lot of projects already having deployed Ceph.
Yes, lots of people are adopting it, especially over the past year or so. Most use cases these days are centered sort of around cloud, whatever that means to people. So most people are using it in conjunction with things like OpenStack or CloudStack, where they're setting up a private cloud or a public cloud that they want to provide publicly. So they're using it for the S3 compatible object storage service, Swift compatible, or they're using it for storing virtual machine images in the same way that people use S3 and EBS in the Amazon world.
So Sage, I've got some questions for you. I've been working in storage since for the past 13 plus years. And so this is a really, really interesting topic to me. I just want to clarify what you can do with Ceph before I get into some of the deeper questions. So we said object storage, right? So for cloud, what sort of APIs do you support? You may have already mentioned this. I just want to make sure.
Yeah, so there are actually 2 object APIs. One is sort of a low-level native API that Ceph provides natively, and that is a little bit lower level than what you get from the sort of the RESTful APIs. And then on top of that, we build a higher level RESTful object storage service that's compatible with Amazon S3 and compatible with OpenStack Swift. Okay,
great. That was exactly the answer I was hoping for. Now to get to what you can do with it on a lower end, on a block level or a file level. So I could do, like if I wanted to do fiber channel attached to this somehow through a SAN, could I do that? That's question number 1. Question number 2 is, can I set it up like as just plain NFS, share it out to whatever server?
Yes, so there are a number of ways you can access the source system. So at the object level, you wouldn't use fiber channel or anything like that. That's really the block interface, right, obviously. So you can use the native RBD protocol, either by using a recent Linux kernel and mapping a block device, or you can use some sort of gateway. So there's there's the client that's built into the Linux kernel, so you can map it that way. The client is actually linked into the KVM hypervisor, so if you have a virtual machine, it can talk natively to the storage cluster. Or if you need to sort of use it in, I guess, a SAN context, then you would use a gateway that'll re-export it via iSCSI or some other block protocol. So you can do that via the kernel, or you can have a standalone sort of user space iSCSI daemon that'll re-export.
Right. So then once I have that gateway, I can pretty much do whatever I wanted to, right? NFS or CIFS or whatever. Okay.
Right. Although if you're talking about the block layer, then you usually won't use CIFS or NFS.
Right.
Using the file system, then you can use, again, the native Ceph protocol to do it, or you can have a client actually mount it via the kernel or a user space re-export, and then re-export via CIFS or NFS that way.
Okay. And then let's get into some of the other features that storage people typically want to see with these types of systems. So you mentioned one, which is high availability. So I'm really curious about how you do high availability and things like, do you offer global namespace, which for people that don't know is the ability to address, storage across multiple, you're not accessing one particular device. It's actually spread out across multiple devices, but visible as if it were one device from multiple hosts. So do you offer global namespace? What do you do for disaster recovery? All those questions come to mind as a storage administrator.
Yes, so the design goals for the system were to operate at petabyte scale, which at the time was really big. Now it's more like exabyte scale. But what that means is that you have to be able to deal with issues like node failure and disk failure and so forth at an architectural level, and not just sort of paper over them with doing high availability failover pairs or something like that. So that means that Ceph is replicating all data in the system. All objects are replicated on multiple nodes, and it's constantly monitoring the health of those nodes. And if any node fails, then it'll use the remaining replicas and build new replicas of those objects and so forth. So that's sort of the high availability piece. And it takes pains to make sure the data is distributed intelligently across racks and different power circuits and all that sort of thing. And then the second piece is, having sort of a single management interface, a single global namespace. And the goal there is that if you have, petabytes or exabytes of data, you can't have this situation where you have, 100 separate, large devices and have to manage the placement of data across them. You want the system to deal with that on its own, so that you don't have to worry about where your data is stored. The system distributes it for you. And that's also fundamental to the architecture. So on the file system side, you get a single global namespace, a single root directory, and then all your files are there, and that's the entire cluster. On the block layer, again, you have, you can create separate pools of storage, and then they're accessible from anywhere that can access the cluster. And the final piece that you mentioned is disaster recovery. That is a work in progress at the moment. So the system was originally designed to operate within the confines of a single data center. So there's this assumption of low latency links across all nodes, replication of synchronous and so forth. So we really had, these supercomputing installations in mind at the time. But as it's become clear, as we sort of move into the larger world storage and people start adopting this, disaster recovery is key. And so what we're working on for our next release, Dumpling, which will be later this summer, is a DR solution for the object gateway. So, much like S3, where you have sort of two pieces of it. There's the federation piece, where you have buckets that are in multiple data centers and sites, and you can choose where they're stored. That's sort of step one. That's what Amazon gives you with S3. But the second piece is the DR component, the disaster recovery component, where you can say this bucket or set of buckets or everything at the site is also replicated in another data center asynchronously, so that if a flood takes out that whole data center or something, then you can fail over to another data center that has everything, modulo 1 minute of updates or something like that.
Right. So that's great that you're working on that. And then, but for now, I want to go back to one thing that you said, which was right now it's designed to work in a single data center, basically. And it sounds like when a write comes in, it's getting written twice. And that's happening synchronously before the acknowledgement goes back to the host?
Right.
Okay.
Right.
That is really, really cool and really crucial for, because you never know when you're going to lose a disk drive. You never know when something's going to fail. So the fact that does that automatically right now is absolutely wonderful.
Yeah, and it's a choice. So there are systems that have eventual consistency that are sort of built for a different type of use case.
Right.
In our case, we built the system with, or the object storage system in particular, with the aim of building a file system on top, where consistency was the most important thing. You didn't want it to have something that was corrupted or out of date or something like that. And so that was an absolute requirement in our case.
Yeah. Now, what happens when there's a node failure? How does the traffic get directed around the system to know, oh, this node that I was just accessing a video file from, for example, went down, and I need to pull this from another node in the system?
Mm-hmm. So the object storage system is designed to be highly scalable, which means that there's no sort of gateway node that you're going through before you reach the storage nodes. You talk directly to one of 10,000 or all of them in some cases. So the basic idea is that the clients are able to calculate which node they're talking to in the cluster based on the current cluster state, and then all the nodes in the cluster are constantly monitoring each other for failures. And if there is a failure, then that failure is spread throughout the cluster via gossip and shared to the clients via sort of incremental updates to what their view of the cluster state is. And so generally when there's a failure, it'll be noticed very quickly because there are like 100 other nodes that are pinging that node that recognize that something went wrong. And then they immediately share that information with everyone that they're talking to. So from the client's perspective, it'll ordinarily find out about a node failure and redirect its traffic to a different replica before it actually has to access that node. Although in certain cases, it'll actually hit the failure right as it happens, wait a second for the system to decide that node actually is dead, and then traffic will get redirected to another node.
That's awesome, because I think it's important for people to understand that the way applications typically work is they have a timeout feature. Almost every application has some sort of a timeout, and in my case, when I was working with the Oracle databases a lot as a customer, it was 30 seconds. And if you didn't get a response in 30 seconds, you would fail, and the application a lot of times would crash right there. And so this is really crucial. The synchronous, all these things that we're talking about, the technical jargon here, the synchronous writes, the fact that there's no gateways. I mean, this is all really, really important, and that's why I'm kind of drilling into this. So I've got a couple more questions, and I don't think Randal's going to be able to break in here. But the other question I had is, just again, in terms of setting the stage, now that we've covered the basic functionality, is, there are some competitive software out there, and the one that comes to mind most notably is Gluster, which was acquired by Red Hat. And so I'm kind of wondering, how do you differentiate yourself from Gluster or maybe other systems out in the marketplace?
So Gluster is probably one of the ones that we run into most often. Gluster is largely targeting a different use case. So it was designed to be a scalable file system and to stripe across multiple nodes. It's a much simpler design, which you can take either as a good thing because it's a simpler system and there fewer things can fail, or a bad thing because it isn't as ambitious in how it tries to solve problems and deal with performance issues. It's a little bit more mature because it is simpler and has been sort of used in production longer, but it doesn't have the same design tenets that allow it to perform well in many of the situations that Ceph will perform well in. The other thing, I think the main difference, though, is that the way that Gluster is largely being used currently and the use cases it's targeting are mostly around file storage. And for Ceph, it has object, block, and file, but mostly we're focusing right now on object storage and block storage because those are the use cases that are most mature in the system and people are sort of deploying right now with all the cloud craziness that's going on. Mm-hmm. And so we actually don't bump into each other as much as you might think.
Interesting. I figured you guys would be head-to-head all the time, just because if you look at the high-level descriptions, they're very, very similar. Mm-hmm. In terms of the fact you both do object storage, you both do block storage. I think the distributed nodes and things like that. There's a lot of high-level similarities, it seems like, and so.
Yeah, I mean, a lot of the things that you would find on a feature list checkbox,
right?
High availability, automatic data distribution, hashing, all that stuff is similar. But the way that the actual systems are constructed is actually very different. So Gluster is largely built around these sort of pluggable translators, which is a really elegant model, but doesn't always lend itself to sort of efficiency for all those use cases.
So, because I hear this a lot, comparisons between Gluster and Ceph, especially when you read if you go to just the basic web pages and you look at the description. I mean, you guys both do object storage, you both do block storage, distributed node architecture, and all this stuff. So, I mean, it just seems like from a high level, at least, it looks really similar. But I mean, it sounds like there are some considerable differences.
Yeah, so if you look at sort of the high-level feature list, you find a lot of the same things. These are sort of what you'd find in a checkbox feature list on a website. Highly available object storage. Just scale out, the most overused term in the industry, misused, I should say. But in reality, the architectures are actually very different. So GlusterFS is designed as a file system, first and foremost, that has all these sort of pluggable layers that let you add, replication, data distribution, striping, and so forth. A very elegant architecture, actually, but the way that it's put together sort of lends itself towards certain use cases. The Ceph architecture sort of flips this on its head. So instead of taking a file system and making a block device a really big file and objects files and so forth, Ceph is actually based on a much lower level abstraction, a distributed object store with various semantics that actually are somewhat similar to files, but actually also have many similarities to like a NoSQL database or something like that. And then on top of that sort of low-level object storage primitive, we build all kinds of services, whether it's an S3 compatible object store that's optimized specifically for S3 semantics, or a block device that's just striped over objects and sort of optimized for that, or a POSIX file system that has a whole other layer of complexity for managing files and directories in the namespace. And that's a pretty typical pattern. If you actually look at a lot of the enterprise vendors, again, you find that they built a distributed or parallel file system 15 years ago, and then now they find that they need to be able to satisfy these virtual machine use cases with block devices and object storage, and so they just make those things files using their existing technology. Ceph, on the other hand, builds a distributed object store and then layers these higher level services on top of that.
Yeah.
So it's a different approach to the problem. We like it. We think it works very well.
Well, let's talk about some other comparisons too. I mean, we just had one from the chat room talking about Lustre. And then there are other comparisons I want to make as well, just so people are aware. Things like ZFS file system, for example, which I'm intimately familiar with, and other standard file systems. How would you, at a high level, describe the differences between what Ceph does and those types of systems?
I'll start with ZFS because it's the most different. The key thing to recognize with ZFS or Btrfs or even XFS, any of these other file systems, is that they are local file systems. They're designed to have a single host computer accessing one disk or many disks, but it's really managed by a single node. So they're scale up and not scale out. Lustre, on the other hand, is actually a scale out system. I would call it a parallel file system. It's designed to run with 1,000 different object storage targets, storage nodes, and then each of those has maybe 500 or 1,000 disks behind it with some big disk array. The key difference with Lustre, at a high level, the architecture looks very similar. When you look at the file system, there's metadata servers and object storage servers and so forth. But the main difference with Lustre is that it's designed for high performance workloads, but it is not designed to be fault tolerant. So you're striping across these storage nodes, these object storage targets, but each one usually has a pair of servers that are in sort of a high availability configuration with a high-end disk array that handles all the failures on the back end. In contrast, Ceph is replicating across all of its servers. So the idea is that any one of those nodes can fail, and they can be built out of commodity, relatively inexpensive components instead of these high-end components that are much more expensive.
Yeah. So let's talk a little bit about performance too. So do you load balance at all for performance? I mean, because depending, I guess, on the architecture, I mean, you could have different performance loads, obviously coming from different hosts, and you may need to, for example, you don't want your top 5 heavy-hitting hosts all going to 2 storage nodes, when you've got 100 storage nodes sitting underneath you, right? You want to spread that load out so you get good performance. So how does that work?
Right. It depends on which part of Ceph you're talking about. So if you're talking about the low-level distributed object store, the strategy there is to have objects be relatively small and to distribute them randomly across lots of nodes. And so just by the virtue of having trillions of objects randomly distributed, then the load will on average be very well distributed. In the cases where it's not, where you have a small number of very hot objects, there are provisions to sort of correct around that. But in general, we rely on sort of the randomness to distribute workload. Once you start talking about the file system, then the situation is completely different. There we have a separate cluster of metadata servers that are keeping track of the file system namespace, the files and directories, and they're doing something totally different. They're looking at essentially a heat map of the file system namespace and seeing which parts of which directories and parts of the file system are receiving the most traffic. And then based on that, they automatically redistribute responsibility for those parts of the namespace across available metadata servers. And the idea there is that for example, in HPC environments where you have these batch jobs, you'll have one workload, one application running that's hammering a particular part of the file system, and that'll automatically get distributed across all nodes so that it's balanced and you're sort of maximally utilizing available resources. And then 2 hours later, a new job will kick off that's completely different, running a different part of the namespace, and then that'll get redistributed. And so you're always sort of using what's available.
Great, that's awesome. And then what about physical resources in each node? I mean, I know we're talking about scale out, right? Big buzzword. Scale out architecture instead of scale up architecture. But like if I add more memory, I mean, things are obviously going to get cached into memory before they go out. And I'm just wondering, like as far as the memory architecture goes, how is that handled? Do you recommend putting a lot of physical memory in these nodes, or putting flash devices in these nodes even to be used as cache? I'm just kind of wondering how that works out.
Well, the system itself is agnostic, so you can run it on the slowest SATA disk you can get, or you can run it on Fusion IO drive, expensive devices, and it'll work. Your performance will vary accordingly. The sweet spot tends to be a combination of the two. So what most people are doing today is they're deploying nodes that have a bunch of SAS or SATA disks, and then they also have a bunch of SSDs. And we use the SSDs for journaling and for caching and so forth. And then they're storing lots of data, and so the disks are there because flash is too expensive for a lot of people. So that's sort of the typical configuration. The more RAM you pile into the system, the better performance you'll get because they'll cache more things locally. And because of the sort of peer-to-peer distributed nature of the object store, Ceph often uses RAM for managing recovery metadata and so forth. So having a large buffer of RAM in your storage nodes is always a good idea.
Right.
You get better performance in the general case, and in recovery, you have a lot more breathing room.
Right. And as every storage administrator knows, typically the answer to any performance question or how things will work is it depends on the workload, right? I mean, that's
exactly.
I mean, it really is true. It depends on what your workload is. A database workload is going to operate very differently than a web traffic type of workload, right? So,
right.
And even the types of files, how it accesses the files is quite different. So talk about the applications. What applications do you typically see running, or what are the best applications to run on Ceph, or where has it been used most often?
Yeah, so the two use cases that are most common are building a RESTful object store that's compatible with S3 or Amazon Swift. So these people are setting up a private cloud inside an enterprise, or they're setting up a public cloud because they're a service provider, and they want to provide that S3 RESTful object storage service to customers or to some application that just needs to dump data and objects. And in that case, usually the latency typically is less of a concern, and usually the objects are larger. It's sort of bulk data storage, and so usually those people just use lots of SATA disks. Maybe they'll use SSDs to improve write performance somewhat, but it's less critical. But it tends to be larger writes, colder data. And the other most common use case is storing virtual machine images. So again, people are setting up these public-private clouds. They have lots of virtual machines. Each virtual machine has a disk drive that it's booting off of. That's a virtual disk stored in RBD and Ceph. Those workloads tend to be lots of small I/O because they're actually, those virtual machines have file systems. They're doing all these small writes and reads. And then those workloads running on top of either pure SSD or a mixture of SSD and disk with more SSD than you would otherwise have in an object workload tends to work very well. The most successful users, I think, have just gone all SSD, and they seem to be very happy with that.
So I'm listening to this, real fascinated by all this, and obviously Aaron knows a lot more about it than I do. But I do have a few questions. I'm sort of curious, can Linux boot off of this file system?
That's a good question, actually. That just came up on the mailing list a couple of days ago. In principle, yes. There's nothing preventing you from doing that. You would have the bootloader would launch in an initRD that would map the image and then mount the root file system and then boot off of it. RBD is a natively supported block device in the kernel. There's nothing sort of magic about it. There's just sort of that bootstrapping of knowing which image to map and then actually triggering that mapping process. But I don't know anybody who's actually done it.
Because one of the things,
in principle, it should work.
Yeah, one of the things I really like about FreeBSD is that it's not only a familiar BSD for me, but it also boots natively off ZFS, which I found to be a very fascinating thing. So I actually have my entire file system as ZFS completely. And this sounds like it's ZFS on steroids. And I know that phrase is overused, but it'd be kind of cool if I could boot something directly off of this. Speaking of that, though, what compatibility do you have with other operating systems, like FreeBSD or OS X or something like that?
On the server side, actually building Ceph storage nodes on other operating systems, there was somebody that contributed a whole bunch of patches porting to FreeBSD. I don't remember what number it was at the time, maybe a year and a half ago, and we merged all those changes. But we don't regularly build the project on other OSs, so I don't know if those changes, if it still builds or if it still works. Recently, people have been running Ceph on top of ZFS on Linux, which actually has generated quite a bit of interest. So that's possible. As far as running the server side on other operating systems, in principle, it's possible. It's almost all entirely in user space. There's no special kernel support. It's just a matter of making sure all the sort of Linux-isms that we use are if-def'd out appropriately. And so that's something that could be done, but hasn't actually been done yet. On the client side, obviously, it's a totally different story. So Linux has native support for mounting the client or the file system in the block device. But you can also access it through iSCSI. You can re-export the file system via NFS or CIFS. And there are patches to have native Ceph support in Samba, for example, so you can do that very efficiently and easily. There's also a user space NFS server that's gaining a lot of traction called Ganesha. And there are also patches to re-export Ceph via NFS via that project as well.
Awesome, cool. And earlier we were talking about the connectivity of the client to get the information at the lowest level and had to use the algorithm to figure out which node to talk to. Does that mean that every client that wants to use this has to have access net connectivity to all possible servers in the cluster?
Yes. The assumption is you have some sort of reasonably flat network architecture so that the client can access everyone. It is possible to have the client behind NAT, so all the connections from the client to the server are outgoing, and that works fine. But it does need to access all of the servers.
And if the cluster gets disconnected, is there some sort of resynchronization protocol when they wake back up again, or does that screw things?
It depends on how long they're disconnected. So if it's a short period of time, less than 5 minutes, I think is the current default, then it'll reconnect and continue. As for the file system, if a file system client is disconnected for a long period of time, it'll get booted out and it'll have to sort of reconnect. For the other protocols, for the block and object storage, they can wait indefinitely. So if the client's disconnected and is trying to write and the cluster is unavailable, it'll just keep trying until the cluster comes back.
So if I have a data center and a separate data center, I guess I have two data centers. Yes, I have two data centers, and I had ensured that there were replicas of every block on both sides. Well, then when it disconnects and then reconnects, it's going to have to figure out who's got the newer stuff, right?
Right. So in that case, Ceph is very careful about maintaining consistency in that case. And so sort of when you have that sort of split brain scenario, which half of the brain, I guess, is able to continue working and which one just waits, is determined based on what we call monitor nodes that use the Paxos algorithm, which is like majority voting, essentially. So if you have only two data centers and they get disconnected, only one of those data centers will sort of continue and be able to write, and the other one won't. And then when they reconnect, it'll resynchronize. But it'll know which one it is because of all the internal bookkeeping that it's doing. Two data centers is actually sort of the hard case because when you have a split, one of them is always going to win. It's always going to have the majority. It would actually be better to have three or more data centers, because in that case you just figure out which set essentially has the majority of the monitors, and those will be able to continue.
And one of the things I saw is I saw a presentation actually on Ceph at the local Los Angeles, I forget where it was, UASC or something like that.
UASC, yeah.
Yeah, okay. And then one of the things I really liked about it that was sort of interesting was the idea of having essentially copy on write on file systems. Can you talk about that and how that works?
Sure. So one of the sort of the overarching goal of Ceph was to provide a lot of the features that you get out of these expensive enterprise systems using something that's purely open source and actually scales and performs well. And so one of those features obviously is the snapshot idea. And so the the low-level object storage infrastructure that Ceph is based on has all these primitives that allow you to do efficient copy on write of objects when appropriate. And so all the various services that we build on top of that utilize that. So for the block device, for example, you can create snapshots of block devices. And that essentially means that when you create a snapshot and then you eventually write to a part of the image that has been snapshotted, it triggers a copy on write on the object store of that particular object. Depending on what file system you're running underneath the Ceph storage daemon, it could be on that particular storage node. It might be Btrfs, it might be XFS or Ext4 or whatever Linux file system you're using. If it's Btrfs, we'll hook directly into the Btrfs copy on write infrastructure to make that clone of the object efficient. If you're using an older file system like XFS or Ext4, then we'll actually just copy the object. Or eventually ZFS, I think we'll be able to do the copy and write too, although that's a work in progress. But the idea is that if you're sort of using the optimal stack, Btrfs in this case, then all of that cloning and copy and write stuff is all very efficient. And if you're using something that isn't as efficient, well, it'll all still work. It'll just be a little bit slower.
Well, and let me make sure I understand this. From the presentation, I think I understood that you would have, let's say you have a 4 gig web server image for a hosting service, and you could launch like 100 of those, and it would just use the same image shared. But if you wrote only maybe like 100 megabytes, that would just be copied, just those 100 megabytes associated with that particular running image.
Sorry, yeah, that's actually another feature. So for the block device, you have these virtual disks images, and one of the features there we support we call cloning, where you can take the common use case is that you have sort of a gold image that's a base operating system install that all the virtual machines are based on, and then when you create the VM, you just clone that into that particular virtual machine's image, and it doesn't actually occupy any data until it actually writes to it. And the same thing when it reads to it, it reads from the original gold image until that data is modified. So that's something slightly different. That again leverages a lot of those same capabilities, but is very important for people in sort of the cloud context. The key use case that we're targeting there is in a lot of existing cloud. Public clouds, for example, when you create a virtual machine, there's this long delay while it actually copies the base operating system image for that virtual machine's initial boot disk. And so launching new instances is slow. Whereas with that clone functionality, it's sort of an instantaneous clone to get the boot disk, and you can immediately starting the operating system and reading from the existing parent, while still having its sort of own, the semantics of having its own disk, even though it hasn't actually copied the data yet.
And I stumbled across this word crush a couple of times. Can you explain to me what that is? I started reading a paper that had a lot of complex Greek symbols in it, and I stopped reading. So,
yes. So one of the key design features of the distributed object store is the way that it places data in the system. So in more traditional systems, if you're storing lots of data, there's this problem of knowing where you put the data. And the traditional model is that you have 100 storage nodes, you pick the best one for this particular piece of data, or a random one, whatever, you write it down, you write the data, and then you have some index that says where that data object is stored, so that later when you need to find it, you say, okay, I need to find object foo. Where is foo? Oh, it says it's over there, so you go there and you get the data. That's sort of the traditional model. The problem is that index of where everything is stored tends to become a scalability bottleneck in and of itself. And there's always this sort of lookup step before you can actually find the data that you're looking for. So what Ceph does, and what a lot of the sort of newer scale-out architectures do, some of the big NoSQL databases, for example, is use a mathematical function to decide where the data should be placed. So you look at the current state of the cluster, how many nodes there are and what their weights are, something like that, and the name of the object, and you do a calculation locally that says, oh, well, that data should go on nodes 5 and 8. And then you can talk directly to those nodes by just doing this sort of cheap calculation. And so Crush is the algorithm that Ceph uses that sort of accomplishes that overarching goal of being able to calculate where the data goes and go directly there and get the right answer without having to store that information. Sort of what distinguishes Crush from other algorithms, usually there's something called consistent hashing that systems use. Crush is a little bit different because it's based on a hierarchy of storage devices. So the idea is that you would say in a large cluster you have lots of disks in each storage node, lots of storage nodes in each rack. Racks are organized into rows, maybe rooms of a data center, and you would sort of build a hierarchy out of all these devices. And then you would define policies about how you want your data to be placed. So, for example, you might want 3 replicas of every object to be stored. Maybe you want them all in the same room at the data center so that the replication traffic is efficient and you don't sort of build this impossible network. But at the same time, you want those replicas to be separated across different storage racks so that they don't share a power circuit. So if you have a top of rack switch failure or a power circuit goes out, you don't lose more than one replica of your data. So you get to have both these important constraints about how your data is placed, and also the fact that you can just calculate the placement instead of storing it and doing. You get sort of the best of both worlds.
Yeah, that sounds great. So I can actually plan for the physical layer, as well as just making sure I have, a certain number of copies, because you don't want them to all land in one rack and then, like you say, have a power failure and you just lost all your data. So, or at least lost access to it. So, so that sounds really good. And those policies, is there a management interface to this, or is there a way to manage those policies and see what's going on? Okay.
Exactly. Yeah. So at a high level, the cluster administrator will specify what that data placement policy should be, and the cluster will just sort of make it so. It'll put it in, and you can define. I gave a simple example. You can define more complicated policies, like I want the first 2 replicas to be in the first data center in separate racks, and the third replica to be in a remote data center. Maybe the first replica should be on a fast tier storage using SSDs and SAS, and the tertiary replicas are on slower, colder storage or something like that. You can sort of dream up your own policies, and the system will just do it.
That's really cool. I've got to ask this question just because I do work for Oracle currently, and so I'm obligated to ask whether database workloads actually run on. Do you have anybody running databases on Ceph?
I'm not aware of people running high-end databases on Ceph currently. There was a vendor who was looking to build an appliance to do exactly that, and so they ran a lot of performance benchmarking, and did a lot of optimization of Ceph on top of Fusion IO drives in their case, and the performance was quite good. We made a lot of improvements over the course of that project, but I'm not sure how many people are actually using it in that sort of tier 1 capacity just yet.
Yeah.
I'm sure most users are currently sort of using it in the cloud space, and half of these virtual machines are probably running MySQL, so their database workload sort of mixed in there. But we don't have a lot of people using, running Oracle on it that I know of.
Yeah. Well, you're certainly, I think you're in the sweet spot. So. In terms of servicing both cloud and virtualization workloads. Cloud, and when I say cloud, I really should say object storage workloads, as well as virtual machine workloads. Having those virtual machine images running very quickly is super important. So, because that supports the cloud, so you can also, it's kind of interesting because you're running the virtual machine images, and then also probably taking in via the REST API storage commands, storing stuff from the stuff that's running on those virtual machines. You can do both at the same time, correctly? It doesn't have to be one or the other.
Right. You can have a single cluster that's servicing both workloads, and that's totally fine.
Yeah.
I think the key thing is that you have a lot of these people are trying to build private clouds within organizations or public clouds, and they need the storage piece. They need the object storage piece, and they need the sort of the EDS competitive product for storing these virtual machine images. And there aren't a lot of sort of credible options for doing that in a cost-effective way. You can buy a lot of enterprise storage devices that are extremely expensive, but they tend to scale out only to a point. There's no credible enterprise product that will, go cloud scale, with thousands of storage nodes. You have to have sort of lots of silos of storage in order to make that happen. And there's nothing or very few options that are open source that let you do that in a cost-effective way. So particularly for a service provider where margins are very important, then you sort of need a software solution that lets you choose your hardware, choose your software, keep it efficient. Yeah.
So let's talk about how you make money, right? You've mentioned this is an open source project, and it sounds like I know Randal's going to be asking some of these questions. It sounds like you're taking in contributions from outside parties and building them into the code. But how do you make money? Is it a support model, or are you actually going out and installing this at customer locations?
It's both. So maybe a year and a half, 2 years ago, it became clear that although Ceph was awesome, in order to really get sort of widespread adoption, particularly from enterprises, you really needed to have a company that was going to stand behind the product and support it for them. And so I guess a year and a half ago, we formed a company called Inktank that is, captures most of the Ceph developers work there, and is really dedicated to delivering Ceph, the future of storage for for the enterprise, for organizations that want to deploy Ceph and need the support and sort of, high-touch consulting and so forth in order to actually manage it in a production environment. So we do everything from supporting production subscriptions. So if you actually have a cluster, we'll help you manage it, make sure we help you deal with any problems that come up. We have pre-production subscription that helps you sort of get up to the production point where you're sort of designing and building your cluster. Then want to make sure it's built on the right hardware, it's going to have the right performance characteristics. And then there's training and consulting and all the rest of it.
And so how does this relate? I see you're the co-founder of DreamHost. Is this the kind of thing that DreamHost would use to host the VMs for the servers?
It is, yes. So DreamHost's new cloud products, Dream Objects, is based on the Ceph object store. And Dream Compute, their OpenStack-based cloud compute product, is also based on Ceph RBD.
Cool. And you're also the developer of the WebRing concept. If that's what I think it is, that's from like 15 years ago?
Yes. Yep. That was high school for me. 1998, something like that. 96. It's a long time ago.
Okay, for those of us that weren't on the web back then, can you describe how tacky it was? Sorry. But
yeah, the basic idea was that instead of having Yahoo go and build this topic index of all the sites and sort of what their categories or whatever, you would have the people who run the sites sort of self-organize into, groups of sites that are related to the same topic, and they would organize into a circular ring structure. So if you found one site about, your favorite subject, you could click onto the next one and find sort of similar content.
And so you sort of invented Crush as the web level already. That's great.
Yeah, well, I think if anything, it gave me sort of a sense of the importance of community around those types of projects. Getting a large number of people who are sort of have vested interest in building something and making it work.
And this was also the only way to find things before we had things like, I think the first big thing was Alta Vista, or was it Lycos, I think was one of the first search engines?
Lycos, Alta Vista, Web Crawler. Those are the days.
Yes. The kids in the audience are now going, what the hell are they talking about? Here I am dating myself again. No, I'm not just dating myself. I'm carbon dating myself. Yes, anyway. Who decides what goes into the next release of Ceph? How does that work? That's
partly me. I'm sort of the main maintainer, so I guess I have ultimate say what goes into the tree and what doesn't. Most of the developers work at Inktank, although there are a number of community contributors as well. But we follow sort of a typical sprint model where we have a backlog of things that we want to work on. The community has the things that they want to work on. We organize into sprints, do all the testing, get it all coded up. And then we have a regular release cadence. Every 2 weeks, we come out with a new release, sort of a development release. And then every 3 months or so, we have sort of a big release that's going to be, a stable release, we call it. That'll be maintained for a longer period of time. So if you're deploying a real production cluster, you'd choose one of those. And then as new features or fixes, whatever, become available, we pull them in. We backport them as necessary, and then march forward.
Now, how much of the contributions are coming from outside Inktank at this point, and how much are still all internally generated?
The majority of the code is still written by Inktank employees, but that's changing quickly. If you look at there's a recent blog post on the Ceph site that summarizes a lot of community stats about the number of participants on the mailing list, that type of community, and also the code contributions. And there's been a huge increase over the past 3 months, actually, just starting this year, where we have significant contributions coming from the community. And the most exciting thing, actually, is that we're just releasing our Cuttlefish release this week, the next couple of days, as soon as I'm done with this interview. And then our next release, Dumpling, we're having a Ceph Developer Summit. That will be entirely online. It's on May 7th, and people are submitting blueprints from the community, and then we'll be discussing them all day on Google Hangouts and so forth to decide what shape these new features are going to come in, who's going to work on them, how the work is going to be divvied up, and then so we can get them into the next Dumpling release, which will be August.
Now, I seem to have saw that you're not at release 1.0 yet. Should I be worried about that? Can I deploy on something that's not 1.0 yet?
The release number is the most meaningless part of the whole process. We started at 0.1 and have been sort of arbitrarily increasing since then. We're on 0.61 right now. There's part of me that didn't want to go to a 1.0 until all of the features that I ever wanted to see in the file system were sort of done. That's clearly a sort of a stupid idea because it's gonna be a while. And my idea of what I want to have in sort of the 1.0 release is changing. And also 1.0 for a lot of people means that it's the very first version and it's probably not very stable. So in the end, the version number is mostly meaningless. What's more interesting is that we started doing these stable releases every 3 months or so, starting with Argonaut and then Bobtail and now Cuttlefish. And those are sort of the versions of Ceph that have been running in production. And the first Argonaut release was last August. Bobtail was around the beginning of the year. Cuttlefish is now. We're now in our third stable release. We still have production clusters that are running on Argonaut successfully without problems. So I would say it's used in production ready, quite stable.
Okay, yeah, it was going to be my next final question about that, which is, okay, it is production ready. We can bet the company on it then.
Mm-hmm. Yeah, I think the only caveat there is that Ceph provides object storage, block storage, and the file system, the file storage layer. The file storage is not used in production yet by very many people, and they're using it in sort of limited use cases. So that's the least stable part of the system. Most people are using object and block storage, and those I would definitely recommend for production clusters.
And at this point, what's on your roadmap? Where are you headed, and what kind of people do you need to help you get there?
Most of the work for Dumpling is going to be around disaster recovery. So that's sort of the next big thing that people are asking for. Multiple data centers and so forth. And so a lot of the work is going to be focused around that. The people we need to get there are mostly developers. So if you want to work on open source, you understand distributed systems or storage, then you should come talk to us, either for a job or to participate in the project. And of course, we're always looking for users and testers. The more people we have out there who are deploying Ceph in their own environments, either just playing around with it or running it in production, the better the product is going to be. The more stable to be, the more bugs we'll find, the more robust.
Cool. And I like the name because it's really Googleable. If I look for CEPH, this is about the only thing that ever comes up. But where does the name Ceph come from?
Ceph is short for cephalopod. It was named by one of my advisors at UC Santa Cruz. I guess the link is the mascot for Santa Cruz is a banana slug, which is a mollusk. Cephalopods are also mollusks, but cephalopods, octopi and squid and so forth, are very smart. They have lots of tentacles. They're sort of distributed. They're really cool. So that's where it's at.
How do people like? I'm really interested in trying this out, and so what I'm thinking is, would I be able to run a bunch of VMs and run like maybe 2 or 3 VMs to actually run Ceph on, and then run another one as a host, just so that I can see the interaction between them? I don't want to go set up a lot of physical hardware to make this happen, but I would like to test it out and just see what happens on the back end.
Yep, you can run it inside virtual machines. It won't be very fast, obviously, and that's not what you would run in the real world, but it's fine for testing. You can run it on a single node. All developers regularly run this on their laptops for doing development. You can run all the server side is really just daemons, so you can have as many or as few on a particular node as you want, or you can deploy it on bare metal hardware. It's whatever works. If you go to the Ceph website and click on the documentation link, there's like a quick start guide, 5 minutes to sort of get a simple system set up and running. So it's quite simple.
Good. That was going to be my next question. Is where do I go to find out information to get that done? The other thing is, I know you talked about upcoming releases, but what actual features, and maybe I just missed it because I was reading, but what actual features can you talk about that are going to be in those upcoming releases? I mean, I know you mentioned you're talking about disaster recovery. What are the big things that you're really working on that you think will really get Ceph to the next level? What are the big barriers you're trying to overcome?
So disaster recovery is the biggest one. For the next Dumpling release, we're going to have a DR feature for the RADOS gateway for S3 and Swift object storage. So you can have multiple data centers. You can have sort of a single unified namespace of buckets, similar to what S3 has in multiple data centers, multiple sites, and also have replication and so forth across those sites. We're also working on a DR feature for the RADOS block device. So that if you have virtual machines that are hosted in one data center, you can have those regularly synced up with another data center so that you can restart those VMs in a recent state elsewhere. We would like to have a similar capability at the low-level object storage layer as well, although that's a bit more in the research experimental realm. There's a lot of work going on around performance and additional data integrity checks. So there's end-to-end checksuming and so forth, so we can verify that we know exactly that the data that we're getting back is the right data. So there's work going on there. And a lot of the work is really around integration. So we've done a lot of work with OpenStack in particular to make Ceph work very well with OpenStack, but there are lots of other cloud platforms out there, CloudStack. There's some preliminary support there, but there's a lot more that we can do. There are other, there are things like Hadoop, lots of people doing big data workloads. There is an integration that exists right now for Hadoop, but it isn't very well tested or deployed currently, so there's a lot of work that we can do in those sorts of areas as well.
Well, we're almost out of time, and this has been a fascinating conversation. I wish I had another hour to keep going into more of the details. We're just striking the surface, I can tell. But is there any one or two things that we didn't cover that you want to make sure our audience is aware of?
Let me think. I think we.
Then let's go ahead and we'll wrap it up. Okay, so
I guess the one thing that might be worth mentioning again is that we're having our first Ceph Developer Summit on May 7th. So for those who are interested in participating in the project, who would like to contribute code or just want to see what we're working on for the next release, you should definitely check out the website, look at the wiki, stop by, and listen into what we talk about. It's going to be very exciting.
And this is virtual. It's not like a physical gathering somewhere.
Virtual, yes, exactly. It's all, wikis, Etherpads, and Google Hangout.
Awesome. That's the best kind of conference because I don't have to travel to go anywhere to get to it. That's really cool. Okay, my fans would yell at me if I didn't ask the standard 2 questions. So what's your favorite text editor?
Emacs.
Yay! Finally one! Yay! I got one this time. But I know I'm probably going to be disappointed in the next one. What's your favorite scripting language?
That's a good question. We built DreamHost on Perl. That was 2 years ago, and that was cool. But I don't do any Perl these days. I've been doing a lot of Python and like it a lot, but I'm terrible at it. So.
What do you mean years ago when that was cool? What are you saying there? Okay. Well, I just had to underline the statement. There we go. Okay. Well, Sage, it's been wonderful having you on. I'm sure this will awaken a lot of people's interest in Ceph now because my audience likes to find out about stuff like this, which is why I bring people like you on. Thank you for allowing us to talk to you today.
Yeah, thanks. Thank you very much for having me. It's been great.
Very good. Well, that was Sage Weil. Now that we got it right. What do you think, Andrew? I'll mess one up and not get the other one right. Did I call you Andrew last week, too?
No. Andrew, is there an Andrew here? Andrew? No? Oh, sorry. Just me, Aaron.
Aaron, what did you think? I know this is really in your area, so you had a fun time chatting. We chatted a little bit in the chat room offline. I'm just, okay. Aaron, what do you think? Let's do it that way.
You could tell I'm really interested in this. I mean, this is something that it's kind of an emerging area for storage. Like storage, traditional storage can be a little bit boring, and maybe, I don't know, hopefully this podcast wasn't too boring for people. But when you talk about storage, people start tending to nod off. But this is one of the few really, I think, exciting emerging areas within storage. The whole idea of object storage for the cloud is really exciting. The scale out and distributed architectures that people are coming up with are really exciting because of the things that they enable people to do. I love one of the things that he said, which was, you can basically architect this at a scale with really very cheap, not very fast devices if you don't need that. But then you can actually scale up within the nodes and add lots of memory and add flash devices or deploy the whole thing on flash and get some really, really good performance. So I love the fact that that's there because that doesn't happen all the time. And the fact that means that the application areas, the use cases expand because of the way that the architecture is built. And so, yeah, it's really, really cool. It's not brand new. It's not brand spanking new, but it's one of the areas that there's a lot of work going into right now. And so I love the fact that this is open source, and it's a hot topic, at least in the storage community. So really very interesting stuff. I can't wait to get home and fire up a bunch of virtual machines and test it out.
Yes, yes. No, actually, that's probably one of the things I'm going to do with it. No, it's one of the things I'm going to say I'm going to do and then never do. Like I do for almost every one of these shows that I find fascinating. One of the things I like, though, is, and I think this was applied to Ceph as well, but I know that when my friends talk about ZFS storage, they talk about the fact that you can use slightly faster but slightly less reliable drives that are cheaper. You just put more of them there. And then the total dollar cost is lower, but your reliability remains high. And here it seems like you'd be able to go up one level from that. You could use cheap drives that are fast and but slightly less reliable on off-the-shelf hardware that doesn't have to be highly reliable either, because you can duplicate your hardware horizontally to make that happen. Is that your understanding?
Yeah, because it's distributed. Now, granted, the cheaper and less reliable hardware you use means you could have a potential for double failures. But like he said, you can actually go in the policies and architect around that. So you can say, I want triple redundancy. Or I guess you could do quadruple redundancy. I'm not sure, but you could up that level of redundancy across the architecture to compensate for the fact that you're using less reliable hardware. It really does let you deploy architecture similar to Google or Facebook. They're writing their own file systems and they're writing their own low-level software to manage all these devices that make up their cloud infrastructure. But this really gives you the tools, or a business the tools, to go do something similar with your own hardware. So yeah, it's really exciting.
And it also seems like this would be the kind of thing that I'm curious to see what kind of adoption there is. Instead of having Google write their own file system, I wonder if it's the sort of thing that Google would go, hey, in our next data center, let's just build it out with Ceph.
Yeah, maybe not Google, but definitely one layer below that. So I don't think Google will be at that point for a while. But for the layer below that, people are thinking, I don't want to hire software developers to work on file systems, right? I want to be a lot more agile than that. So I want to deploy something, get it up and running, and make my business grow on it. And so that's what it really enables.
Cool, cool. All right. Well, we could talk about this forever, as I said. So I'm going to have to wrap it up because we're getting close to the end of the show. So speaking of upcoming shows, there's my Akko transition for the week. Next week, we have Sauce Labs. Sauce Labs is for testing your systems. It's basically all about testing. But rather than just being something like Jenkins, where you're just building stuff inside some sort of VM, there's an option to even test in browsers. Now, most of us probably don't have access to more than maybe a half dozen kinds of browsers. We may not have all the operating systems sitting around. But what Sauce Labs does is provide VMs that have like 160 different combinations of operating system and browser version. And so you basically say, here, test this. And not only do they have an automated testing system, but they also have manual testing, where you can just say, well, I wonder what my website looks like on IE6. And you push a button, and 2 seconds later, there's a VNC window up there, and you're actually talking to whatever website you want to talk to. It's really pretty cool. It's built on open source software. There are components of it that are open source. They're contributing upstream to open source. It's not open source directly. It's a platform as a service. No, not software as a service. What was it? Platform as a service. So you can actually use their infrastructure to do testing. But the relevance for open source people is that they will give free accounts to do unlimited testing of open source software. So if you're building something that's browser related and it's open source, they'll give you a free account to go do that. So it'll be really nice. So that'll be next week. John O'Bacon's going to come on. We're bringing back the bacon. Yes, indeed. It's coming on in 2 weeks. He's talking about the Ubuntu phone. I don't know anything about that except that it's the Ubuntu phone. So hopefully you'll send me some questions to ask. And we just added 4 more shows since the last time we chatted. So we're finishing up the Q2 schedule. We added the Mine EDMS, which is a document management system. I know, enterprisey buzzwordy sort of things, but very handy stuff. And hey, it's Mine. I like the Mine culture, so hopefully it'll be related to that. We also added the Maker, which is a content management system for Macs, which is pretty cool. So you have a full content management system that runs native on the OS X platform, and then you push a button and your website gets all published. I thought it was kind of cool. And it's all open source, so you can actually probably build it on other things as well, anything probably that runs GTK. Also just added Web2 Project, which is a business-oriented project management system. So there's a lot of real commercial offerings in this area of keeping your project on track and making everything work like that. But this is all open source, and I think they also host it as a platform service as well. And then also just added Ansible Works. And I got a lot of raised eyebrows when I added this to the list, because it's like Puppet and Chef, but apparently it scales even better. And there's some really big companies using Ansible Works. do the deployment. It'll do everything from bare metal up to getting the whole operating system running and all that sort of stuff. So that looks really, really cool. I'm really looking forward to those shows. So yeah, Q2 is almost full, but I'm going to be opening up Q3 soon. So you can go to twit.tv/floss, and there's a spreadsheet linked from there that tells us about tells you, it doesn't tell us, well, it does tell us too, tells you about all the upcoming guests and potential guests. And if you have a project that is not on that list and you'd like them to be added, please have the project manager email me, merlin@stonehenge.com, and we will add them as quick as we can. Almost all these projects got on because somebody else that was a fan of theirs and of this show emailed them. So that's really what comes to the top of the list, is everybody that gets emailed to me. You can follow us at Floss Weekly on Google+, and also Floss Weekly on Twitter and Identica, and you'll get immediate updates when I add somebody to the list or when I'm able to schedule a show, and also a pre-show announcement to remind you that we do have a live show. Live show is live.twit.tv at 8:30 a.m. Pacific times on Wednesdays. Typically, occasionally it gets moved around a little bit. Mostly it's there. You can follow me at Merlin on Twitter. You can also follow me as Randal L. Schwartz on Google+. If you have been following me on that, you'll know that I'll be missing the show next week. We have, I think it's Randy Harper and Dan Lynch. I think it's Aaron, you're taking a break next week. Is that what it is?
Yeah, finally. You're finally letting me off the hook.
So I'm on a cruise next week. I'm on the 2013 low-carb cruise because I'm still celebrating the fact that I've lost 45 pounds and 6 inches around my waist and gone from stage 2 hypertension to normal nominal blood pressure, and my lipids are all incredibly good, all just by cutting out carbs out of my life. And that's really helping. I'm going to be around 150 other people that are like that, and listen to about 10 podcasters and bloggers that are experts in this area, including Jimmy Moore, who has had a podcast now for 600 episodes. Oh, my God. I thought our 250 was pretty high, but 600 episodes. And he's running 2 other podcasts now, too. Guy's a podcasting fool, crazy guy. So I think that's all the plugging I want to do. I will see you guys in 2 weeks. Aaron, what do you want to plug?
So a couple of things. First of all, you can follow me on Google+. I'd really like you to do that because I can actually talk to people there. It's a lot easier to have conversations on Google+. So add me to your circles on Google+. Or you can follow me on Facebook and Twitter. I rebroadcast all of the Google Plus stuff out to those networks as well. So if that's your preferred network of choice, follow me there as well. Important information, Maker Faire is coming up in just a few weeks down in San Mateo, out here in California. So if you're going to be out at the Maker Faire, I will be there as well. I should be there both days. And so look me up. I will be at the Open Sprinkler booth. I will be manning or helping to run the Open Sprinkler booth. And Open Sprinkler is really cool. It's open hardware. It runs on Arduino or Raspberry Pi, and it controls sprinkler valves like you might think, an irrigation system. And it's all open hardware, all open software. You can build the kit yourself, which I did. So if you have a soldering iron and you know how to use it, you can actually build the whole thing from scratch, all the components and everything, get a PCB board and just go crazy. Or you can actually order a kit pre-assembled, whatever. But we'll be talking about that, talking about the value of open hardware and the value of open software at Maker Faire. So if you happen to be at Maker Faire, come by, say hello, say you're a fan of the show. I would love to see you. And if you use Open Sprinkler and you'd like to help out in the booth, I'm actually looking for a couple of volunteers. I may be able to get you some passes to the show. So if you use Open Sprinkler, you're familiar with it, you've built your own, definitely let me know. Give me a message via my Google profile, and I'll see if I can use you at the Maker Faire coming up in the middle of May.
Are you going to have like a slip and slide there and actually have a sprinkler set up so people should wear their swimsuits or what?
Yeah, I'm working on that right now. I want to have a really cool demo. I think what it's going to be is, you know, a Android tablet where you can actually control sprinkler valves. And I'm not sure exactly what it's going to do. Maybe it'll be like a big fountain. It can't be too big because we don't have time for that. But, you know, some sort of a display where you can actually set off something, you know, so the kids will enjoy it as well. So it should be really fun. It should be really fun. I don't know what it's going to be yet, but it'll be cool.
That's good. That sounds like a lot of fun. Actually, I wish I could pop up there, but it's not going to be compatible with my schedule, I guess. So anyway, Aaron, once again, thank you for co-hosting, and we'll see you all again next time on Floss Weekly.